Yes.
All right. Hi, everybody. Welcome. I'm so excited to welcome you here to our webinar. So welcome to the Sharing Best Practices webinar on sustainable pipeline design, life cycle cost analysis, and pipeline material selection. This webinar provides tools to assess the complete life cycle cost for pipelines tied to both installation and long-term operation. First, we'll dive into an innovative model developed by researchers from the University of Michigan, Growing Utilities and Engineers, a powerful tool to assess the complete life cycle cost of water transmission and distribution pipelines. And then during the second part of the webinar, we'll explore the total cost equation, or TEC. Today's webinar is jointly sponsored by the New England and Connecticut sections of AWWA. By attending this webinar, you will earn 2.0 TCHs for full participation in today's webinar. That means you stay until the end. And following the webinar, you'll receive an email for the TCH certificate. During the webinar, please feel free to post any questions in the chat or raise your hand after the speakers finish presenting, and we'll have about 15 minutes for Q&A after each speaker. Also, don't miss our next webinar. It's Protecting Public Health webinar featuring EPA's Region 1. We're going to be learning about drinking water program updates for the New England region. This is going to be on Thursday, February 6, 2025, from 10 to 11 a.m. By attending this webinar, you'll get updates from the staff at EPA Region 1 regarding the drinking water program. We'll provide a brief overview of various U.S. EPA drinking water regulations, potential regulatory revisions, and guidance. The topics are going to range from UCMR 5 results, proposed lead and copper rule improvements, proposed CCR revisions, PFAS updates, MDBL 6-year review, and some cybersecurity information. We're going to have some exciting speakers from EPA Region 1. In February, we'll also have the Voice of Water webinar, which is going to be providing regulatory and legislative updates from DC. So this is going to be Thursday, February 20th from 1 to 2 p.m. And this will allow us to learn more about the current state of affairs in Washington, DC, including some new reports on the topics of PFAS and the lead and copper rule as well. At the end of today's webinar, we'll also be hosting a drawing to win this manual of water supply practice, which covers the specification, design, installation, and maintenance of ductile iron pipe and fittings for potable water systems. You have to be fully present during the entire duration of the webinar to be eligible, and we'll select at the end. So today I'm really excited to introduce our speakers. Roy Mundy, Senior Regional Engineer, Sales Operations Group of McWane Ductile. Roy has extensive experience in the waterworks profession, having spent 35 years working up through the ranks at American Water Company to reach the position of President and CEO of AWC's Kentucky American Water Company. Roy then served as the Commissioner of the Kentucky Department of Vehicle Regulation in the Transportation Cabinet before becoming an instructor and Vice President of Advancement with Midway College in Kentucky. At McWane, Roy leads specification development pursuits on major projects and with major utilities, both public and private, as well as supports relationships with those utilities and major consulting engineering firms. Roy is based out of Lexington, Kentucky, and operates throughout the states east of the Mississippi River. Roy has a BS in civil engineering and an MS in engineering management from West Virginia University. He is a registered professional engineer in 6 states. Jeff Hauser. Oh, sorry, was someone going to say something? Okay, I'm going to introduce Jeff Hauser as well, from the New England District Manager at McWane Ductile as well. Jeff started his career in the water industry in 1989 in a small family-run waterworks supply house in Rutland, Vermont. During the next 3 years, Jeff was introduced to the water and wastewater markets and a variety of applications and users. Having been considered a hands-on type individual, these new challenges in developing knowledge in sales and installation of a vast assortment of products began. In 1992, Jeff accepted a position with McWane Ductile, a second generation to work for the company, managing a sales territory of northern New England. Throughout the years, Jeff has been elevated from entry-level sales representative to district manager in New York, and more recently, the past 10 plus years as New England district manager. Jeff has been exposed to several unique situations in the proper application, handling, and installation of ductile iron pipe. So I'm going to stop presenting so our speakers can share their presentations.
Okay. Can you all see that? Are you seeing the slides below?
We can see it.
Just your single slide, Roy.
Single slide. Good.
Yep,
Okay.
your opening slide.
I'm the only one that's seen the one below, so that's a good thing. Very good. Well, good afternoon, everyone, and welcome to our presentation in regard to a framework to evaluate life cycle costs and environmental impacts of water pipelines. And as Cielo mentioned, this particular presentation is actually a presentation developed from research that was conducted by the University of Michigan, Department of Civil Engineering and Environmental Engineering. You'll note that this research was concluded in 2016. And I know that seems like a millennial ago to a lot of people. And what you will find in this presentation, because it basically is their presentation for that particular time of research, then even though the numerical values are of that time, clearly the concepts and methodologies are as relevant today as in 2016. And basically, if you put in today's numbers, you're going to find that you will get the same ultimate result in terms of the research. I might also add, and I'm not sure how many on the webinar today have given presentations at the American Society of Civil Engineers conferences, or specifically the Pipelines Conference. This particular presentation was in fact vetted and verified by a group of 5 reviewers, and then subsequently it was presented at the ASCE conference. And so, having gone through that process myself several times, it pretty much validates the objectivity and the science, if you will, that has gone into the presentation. I did want to, again, on behalf of Jeff and myself, thank the New England AWWA for this opportunity today. This is the contact information for Jeff and I, and we do encourage you, if you have any questions in regard to this particular presentation or any question, quite honestly, about pipelines, we do want to be a resource to you. And we do get quite a few inquiries about specifications, specialty designs, education, and different types of scenarios in terms of the use of pipe for drinking water as well as wastewater. I'm sure that everyone, again, on the webinar is very much aware of the vast infrastructure we have in this country, specifically in regard to our drinking water infrastructure. And of course, with that, I tell people that I do a lot of traveling and stay in a lot of different communities and a lot of different hotel rooms. And not one time have I ever questioned when I would get up in the middle of the night and go get a glass of water out of the spigot and go right back to bed, that I'm going to end up getting up the next morning and not having some sort of issue that definitely can come with drinking water in many, many other parts of the world. So this country and the professionals in the industry, such as yourselves, should really, really be applauded for that particular scenario. At the same time, even though we see in this country iron pipe that is actually serving communities going on 200 years, many over 100 years, our infrastructure is definitely in need of replacement. And the fact is that when that replacement, as it continues to become more and more necessarily, we want to make sure that we put in the proper materials in the ground so that our children and our grandchildren are obviously going to enjoy the effects. So when University of Michigan conducted this research, they looked basically at the key factors of life cycle cost analysis, but they also looked at life cycle assessments when it came to drinking water pipelines in terms of various materials. And as you can see on the screen, they used this approach not only to look at the true value and cost effectiveness beyond the initial price of the material itself, but they also wanted to look at the environmental impact. And I know many of us have seen in our society today, and as a matter of fact, we even are questioned when we give presentations to certain communities. What is your approach, and how do you actually have a positive effect on the environment, not only in producing your material, but the ultimate use of the material itself? And so this is basically how University of Michigan went about this research. When I was with American Water, I grew up through the distribution area of the company. And quite frankly, when it came to water pipelines, the only two areas on this schematic that you see before you that I was really that interested in was the two bottom circles. I wanted to obviously provide for proper installation of the pipe that we put in the ground, and ultimately picking the type of pipe that would be efficiently operated and also give good maintenance service throughout the years. However, the University of Michigan actually took this much further in basically looking at, we're going to look at an entire embodied energy concept from the life cycle assessment standpoint, and then also look beyond the initial material cost of the pipe in terms of how does it really operate in the system, how much maintenance cost does it require, and so forth and so on. So as you can see, this particular life cycle process, this is the approach that they used in developing this research. So effectively, they came up with two modules. One was the life cycle cost module, as you see at the top of the screen there. And the other was life cycle assessment module. Effectively, the LCC looking at those various areas in terms of installing the pipe, operating and maintaining the pipe, and then even the issue of end of life of the pipe, or really specifically estimated service life of the pipe itself. And then in the LCA module, they wanted to look at the environmental impacts. Basically, are there environmental impacts in any of these categories, specifically in terms of operating the pipe after it has been installed, maintaining the pipe? Obviously, inordinate maintenance is potentially an environmental issue, and again, the end of life when it comes to the pipeline material itself. Now, this particular research study was conducted focusing on, number one, two materials. Materials of ductile iron pipe and materials of PVC pipe. This particular approach, you could actually put other alternate materials in those categories. You could look at steel pipe, you could look at PCCP pipe, you could look at FRP pipe. But the reason they looked at ductile iron and PVC was that ductile iron and PVC are the most prominent two materials used in the drinking water industry in this country. They also specifically looked at two diameters of pipe, 8-inch and 24-inch. 8-inch because, again, 8-inch diameter pipe is the most prolifically used diameter of pipe that is sold in this country. And 24-inch pipe representing basically a higher diameter or larger diameter of pipe that has certain attributes toward the transmission systems within a utility. They also looked at the total life cycle cost of ownership. They also looked at CO2 emissions going back to the two modules that I had mentioned before. And then at the end, they conclude their evaluation of the LCCA and LCA. Now, the key assumptions they used for this particular research, first of all, they did conduct it in Michigan. It could have been conducted basically at any point across the United States, actually. They chose 1,000 foot of pipe, 1,000 feet of pipe as being the base length for the pipe itself. As I've mentioned earlier, they were looking at both 8-inch and 24-inch pipe. And they also looked at a project lifespan of 100 years. I'm going to get into why they chose that particular number later in the presentation. Also, along that same line, which I will again get into in terms of how that was determined, they looked at the fact that the service life for ductile iron pipe was 100 years, that a PVC pipe was 50 years. Now, I can assure you, and quite frankly, in the presentation that's coming after this one, this is all going to be cleared up because we will have current numbers in that presentation. But as you can see, these numbers obviously are 2016 numbers. But the reality is, even using today's numbers, it's just the variation and differential of the numbers that really play in, whatever the numbers may be. And of course, the discount rate they used was 2%, inflation rate 1.9%. Only we would wish it was 1.9% right now. And also, the cost of electricity, I used to tell people several years ago that that was probably a cost of electricity that in fact could mirror the electric costs in Kentucky or even West Virginia, because it was a lot of coal-fired electric to get the electric cost down to that low number. Typically today, most utilities are in the range of 10, 12, even 14 cents per kilowatt hour across the country. And once again, when it came to design inputs, we've already talked about the diameters of pipe that are going to be looked at, 8-inch, 24-inch. Also, when it comes to the C factor in both ductile iron pipe and PVC pipe, respectively, they use 140 for ductile iron pipe, 150 for PVC pipe. Pump efficiency, 70%. In the flow criteria, they used 1,000 GPM for 8-inch pipe and 6,000 GPM for 24-inch pipe. Once again, getting into the concept that your larger diameter mains in many systems, and of course that varies depending on the size of the system itself, are transmission mains with larger flows, many of them coming straight out of the plant. So let's come back to the modules and more or less kind of go across the subject line of the LCC module. And the first thing that the University of Michigan looked at was the issue of installation of the pipeline material itself. Cielo mentioned the fact that there was going to be a winner today of the M41 AWWA standards manual, a manual I've got right here next to my desk. And quite frankly, I frequent it quite often. If you look in that particular manual, you will see that there are 5 trench types that are identified in the M41 manual. Basically, type 1, type 2, type 3, type 4, type 5 trenches. And specifically in the manual, it goes pretty much in detail in terms of how each trench type is defined. But in reality, the type 1 trench is basically a trench where you excavate the trench, you put the pipe in the trench, you take the native soil, which should be acceptable and compactable and so forth, and place it back in the trench and properly compact it. That basically is a type 1 trench. And then as you move toward the type 5 trench, you have to then utilize materials that are not native soil, typically select materials, whether it be granular materials or special select mixed materials. Now, the purpose of these trenches and the relationship it has to the pipeline that goes into the particular trench is the fact that when a pipe goes in a trench, and many of you on the webinar today going through your soil mechanics and engineering school may remember the names Marston and Spangler, but they basically came up with the concept that when a pipe goes in a trench and you have backfill that goes on the pipe, which is a load, and then you may even have vehicular loading going across the trench, which creates a additional load, maybe even an impact load, then that load is transferred to the pipe itself. And when it is transferred to the pipe, then there is a maximum deflection that that pipe can have prior to concern of leaking or failure. The maximum deflection equation, which again will be in the next presentation, is pretty simple. The deflection of the pipe is equal to, in the numerator, the load that is coming down on the pipe, and in the denominator, the stiffness of the pipe and the stiffness of the soil. So basically, if you have a very stiff pipe, you can have less stiff soil and vice versa. Therefore, as you move from the type 1 to the type 5 trench, then obviously you get a stiffer trench as you move from 1 to 5. That stiffer trench helps hold in that pipe in the trench if it seeks to go oval, if you will, or deflect, because it's a stiffer soil. And as you can probably imagine, the stiffness of ductile iron pipe is geometrically more than the stiffness of PVC pipe. So effectively, when you look at providing a trench for ductile iron pipe, many times a type 1 or type 2 trench can be used when looking at a trench for PVC pipe, having to establish that high soils modulus E prime for PVC, because it must hold in that flexible material from deflection. You have to go to a type 4 or even usually a type 5 trench. So what does that mean? Well, I'm not going to get into detail here because I'll get into it actually in the next presentation. But here is an example of that very scenario from an actual contractor who lays both PVC pipe and lays ductile iron pipe. And by the way, this contractor is an engineer, a PE gentleman that I worked with at Kentucky American Water Company before we went out and started his own firm. And so effectively, when he puts in PVC pipe, then he has to excavate the trench, haul away the spoil, bring back select material to provide that E prime, because he doesn't want to come back and start fixing leaks at the spigot end of the pipe going into the bale, because that pipe has deflected too much and it's starting to leak, and it could even go on to failure. So with that, in Kentucky, and this is in Kentucky, when he lays ductile iron pipe, Kentucky has good soils, at least in central Kentucky. He excavates a trench, puts the pipe in the trench. By the way, the trenches are all not under the road, but behind the curb. And he uses the native soil to backfill. When he puts in PVC pipe with all of the work he has to put into it and extra cost for select material, he adds $3.95 to each foot of PVC pipe he puts in, over and above that of what he would add to ductile iron pipe for this particular scenario. So now let's look at the issue of the operations of pipeline material after it goes in the ground. I know in many scenarios that I meet with engineers and utilities, when I bring this particular subject up or even present this slide, a lot of times you kind of get deer in the headlight looks of saying, what does energy have to do with pipeline material in the ground? I can understand pumps, I can understand motors, I can understand lighting, but what does it have to do with underground pipeline material? Well, I'm sure that you're aware of the fact that if you have a larger inside diameter of pipe versus a smaller inside diameter of pipe, and using the common equation Q equals VA, Q being quantity, V being velocity of the water in the pipe, and A being the inside area of the pipe. If you have a larger inside area for the pipe, you can have a lower velocity to obtain the same Q factor. So therefore, on the other hand, if you have a smaller inside diameter or area of pipe, and you need that larger V to equal that same Q, then to increase the velocity of the pipe, typically you have to have energy applied, i.e. through pumping. So the University of Michigan basically took this concept and using these particular assumptions that you see on the screen, basically using the Hazen-Williams formula approach, identifying head losses per 1,000 foot of pipe, and also identifying, obviously, the effect that the larger inside diameter has versus a smaller inside diameter. You see the V equals QA issue, Q equals VA, but here V equals Q over A. And then they extended that through identifying the head loss because of that inside area concept to what is it going to cost in electric cost to bring those two components back equaling one another in terms of the diameter differential. And then from there, from a point source energy cost, what is it going to be in terms of the present cost of energy for, let's say, 1,000 feet of pipe under a particular pumping scenario? Those results are going to be later in the presentation. So now along the top line, we look at the issue of end of life. Basically, what is the estimated service life of these particular materials that are being compared, and how was that determined? And of course, when you take one asset in a water utility and that asset lasts longer than another asset, then you have 2 or 3 advantages. One being the obvious advantage, you don't have to replace the longer lasting asset as many times. So therefore you can use your capital dollars more wisely and have more of them to use. From an accounting standpoint, at least in terms of a private water utility, depreciation cost is a operating cost. It's a cost that is embedded in the rates, and those rates are charged to the customer. Obviously, if you have a longer lasting asset and that depreciation can go over many more years than another particular asset, it's kind of like a 15-year mortgage or a 30-year mortgage. The customer actually sees less of a water bill in terms of coming back to put in dollars to replace that asset because it doesn't have to be replaced as many times. So the first place that the University of Michigan turned in terms of looking at estimated service life in regard to these particular materials was AWWA. And I don't know how many, again, on the webinar today have read or seen the Buried No Longer report that was published by AWWA. Actually, one of the first reports that came out that named the T word, the $1 trillion word, in terms of just replacement of water infrastructure in this country. But in that report, they have charts that list estimated service life of various materials in various parts of the country at various diameters of pipe. And with that, specifically in Michigan, if you look at the chart, and as you can see on the screen, ductile iron pipe is estimated to last 105 years, pretty much across the country, whether it's in Michigan or other places. PVC pipe is estimated in the report to last 55 years. So to validate further the AWWA report, as most academians do, which they should, having lived in the academic world myself for a few years, they did go to the AWWA Buried No Longer report, but they also went to other particular reports and research and researched that and came up with the fact that the service life for 100 years for ductile iron pipe and the service life of 50 years for PVC pipe was a valid assumption for them to use in this research. So now we're going to drop down to the life cycle assessment, the lower module that we see. One of the things, again, that you look at, not only in life cycle cost, but in life cycle assessment, is the fact that when you put a particular facility in the ground, obviously, not only how long is it going to last, but what is it going to cost me over that particular period of time after I have installed it. And so the University of Michigan, in their approach, as you can see on the screen, they went to several sources. They did some surveys of utilities in terms of what type of pipe did they have in the system, what type of, shall we say, performance did they get respectively out of each type of pipe. And for the sake of this research, they did not include asbestos cement pipe because it's no longer being made and so forth. So effectively, they narrowed it down to cast iron or gray iron pipe, actually, ductile iron pipe, and of course, PVC pipe. And as you can see on the screen in the particular categories, effectively, the cast iron pipe did, in fact, show quite a bit of required maintenance and repair, but this pipe is probably already 80 to 100 years old. And so therefore it is nearing its life cycle end. When it came to PVC pipe, however, which PVC pipe is still somewhat of a youngster when it comes to the type of when it was first developed and really prolifically used in the water industry compared to iron pipe, then you see almost equal numbers in terms of required repair and maintenance when it came to PVC pipe. And yet, when you look at the ductile iron pipe, which is the purple in the chart, then those numbers are very, very significantly lower. So, is somewhat of a summary in terms of their analysis of PVC and ductile iron pipe for the two diameters that they were looking at, both 8-inch pipe and 24-inch pipe. Looking first at the life cycle cost analysis, they developed graphical information in terms of basically the savings that were evident with ductile iron pipe over that PVC pipe throughout a 100-year period. Now, that savings was predicated on pumping. Basically, how much water are you pumping? Because the more water you are pumping, then you derive more energy savings because of the larger diameter of ductile iron pipe versus the smaller diameter of PVC pipe. And so, as you can see on the graph, starting both at 0 as you move from left to right, then effectively you see that as the pumping increases, the savings for ductile iron pipe gets to be more and more as the first 50 years goes by. Then, because of the estimated service life, and when you take the true value of present worth, then technically you have to replace the PVC pipe at the end of 50 years because it's only going to last 50 years. And yet ductile iron pipe continues to be in service for that next 50 years. So you have the cost of replacement. That's what jumps the graph up in the middle. And then you continue to have the savings in terms of operation costs, primarily due to the issue of energy. In doing the same analysis for 24-inch diameter, then you really come out with the same configuration when it comes to the graphical data. However, you can see obviously higher types of savings, a little more narrow process at the beginning, but it widens out as it gets toward the 100-year mark. Now we come back again to the life cycle assessment module. And this is where the university of Michigan specifically got into, if you will, the carbon footprint. The carbon footprint is something that honestly, we of course serve the entire country. And so our folks out west and in certain areas, even in New England in the Northeast, people are very concerned about the issue of the carbon footprint in terms of sensitivity to the environment. Well, there really is a direct relationship, as you know, between the carbon footprint or CO2 equivalents and the kilowatt hour of energy. And if you lower energy costs and you lower the creation of the energy, and by lowering the creation of the energy, then the carbon footprint that is necessary to create that energy is lowered as well. So again, the University of Michigan took this particular approach, looking at not only the operational costs in terms of the carbon footprint by using a smaller diameter pipe rather than a larger inside diameter pipe, thus creating more energy consumption and carbon footprint, if you will. But they even went back to the very, very beginning in terms of looking at the embodied energy of both materials. Now, ductile iron pipe, even though years ago and even overseas today is made with ore and a very, very messy and non-environmental approach to producing ductile iron pipe. All of the ductile iron pipe made in this country is made basically with scrap iron. Even more specifically, primarily automobile parts, even though there's other scrap mixed in. And so therefore, it is basically a 90 to 95% recycled product. And the other good thing about ductile iron pipe is, even though normally when you abandon a pipeline, it is too expensive necessarily to take it out of the ground and recycle it, ductile iron pipe can be recycled. On the other hand, PVC pipe really cannot be recycled. And by the way, PVC pipe is, I'm sure you're aware, is made with petroleum products. And so it has the direct effect to the petroleum market. So along that line, as you can see here, University of Michigan determined that the embodied energy for ductile iron pipe was much less than the embodied energy for PVC pipe in regard to the carbon footprint. So graphically, when you take the operational cost for 8-inch pipe and 24-inch pipe, and then you take the embodied energy cost for 8-inch and 24-inch pipe, you can see graphically this is the findings in terms of the carbon footprint, respectively, for ductile iron pipe and for PVC pipe, wherein again, ductile iron pipe comes out well at the beginning. So I might So the conclusions that the University of Michigan came to as a result of this research, which I think was about 18 to 24 months of research prior to the release of this paper, basically was that you could, number one, have a framework to look at comparing different pipeline materials in terms of life cycle cost analysis and life cycle assessment. And in the main conclusions, rate of pumping significantly impacts total life cycle costs and emissions. Initial cost of the material does not necessarily determine the total cost and value to the customer. And emissions during the operational phase are more significant than the embodied production issue, and that PVC pipes do have the highest environmental impact.
Hey, Roy, I see we've got a question in the chat.
Okay.
I'll read it to you.
Okay.
In the life cycle cost analysis of PVC versus ductile iron, the C value of ductile pipe generally decreases as the pipe gets older. Was the C value change considered?
Very good question. And I appreciate the question because that comes up. Matter of fact, I think it's even going to be noted in our next presentation. The fact is the C value of cement lined ductile iron pipe does not change with time. The tuberculated pipe that many people see, and I'm sure many of you all may have seen in water systems wherein there was a significant decrease of diameter in the pipe because of tuberculation. Tuberculation does not occur if the pipe is cement lined. Now, how do I know that? Basically, not only does the Ductile Iron Pipe Research Association conduct tests all across the country on cement lined ductile iron pipe that is 20, 30, 40 years old, and basically come up with the same C factor today as when the pipe was installed, which is usually even a little higher, by the way, than 140. But specifically, 2 years ago, maybe 3 years ago, the Ductile Iron Pipe Research Association went to the very first cement-lined cast iron pipe that was installed in this country in Charleston, South Carolina, which was in 1922, 100 years ago plus, and effectively ran a flow test on that pipe. And that pipe C factor came out to be 138. So the myth is that iron pipe does tuberculate and diminish hydraulically if the pipe is cement lined, and basically even gray iron and cast iron pipe has effectively been cement lined since 1930s or so, then you're not going to see any diminishment of the C factor.
Hey, Roy, I've got a second question.
Okay.
PVC, are there any concerns with microplastics?
Well, that is another extremely good and timely question. Number one, and I would encourage you all, and we actually have a presentation on this in itself too, even though it's kind of in the embryo stage, because we want to be extremely objective and truthful and transparent. As you probably know, first of all, vinyl chloride has been listed on the safe drinking water elements list, shall we say, as a toxic substance for many, many years. In December, the EPA moved vinyl chloride from that list into the top 5 toxic substances list for review. And then just, I want to say 3 weeks ago, after the initial phase of evaluation and public comment, vinyl chloride has now gone to the second phase with EPA, where they will now, over the next 2 to 3 years, evaluate the human health effects of vinyl chloride. So number one, the key substance that is used to make PVC is moving in the same direction as, quite frankly, you've seen lead and copper and even asbestos cement pipe move. And my experience has been, having been with American Water and going through regulation change after regulation change throughout the years, and they never get lower. They always get higher once EPA kind of gets her claws into something. And it will change depending on administrations and all that, but eventually it will come to the point there will be an MCL, and that MCL will usually create a lot of money and a lot of issues. Now, that's vinyl chloride. And yes, they're going to look at production of vinyl chloride. They're going to look at transport of vinyl chloride. They're going to look at vinyl chloride. However, there have been studies, one not too long ago in Poland, as I understand it, where they are now seeing, because we can measure things so minutely now, even in terms of parts per trillion, which are looking at PFAs on, where there has been leaching or leachates from PVC pipe in that regard. And so if you marry those two over time, then PVC pipe, and again, it, may or may not happen in my lifetime, but it's going down the path like so many others have. And so it should be concerning to people who are prolifically using that material to at least really stay close to that research. Any other questions?
That's all I have from the chat, Roy.
I had another question for you, Roy, if anyone else doesn't have any.
Sure.
What are some of the key components in the proper bedding of underground pipelines?
Well, quite frankly, it really, and honestly, we're going to get into this even a little more in detail in the next presentation. But to answer your question, you have number one, when you it even begins before you dig your trench, because basically we get called, as you might imagine. Jeff has gone out on probably thousands where people call and say, hey, your pipe's leaking. You got to replace this pipe. And we say, well, let's talk about that. And then all of a sudden we find that they first of all rolled the pipe off the truck on a cement paving or something and didn't unload it properly. Secondly, they did not lubricate the gaskets properly. They did not align the pipe properly when they were putting it in the ground and so forth. So you got to do all those things properly before you even get to the excavation itself. But the excavation, clearly, you want to try to have a smooth trench. You want to take away what we call the local stressors in terms of protruding rocks, in terms of damaging the pipe before you put it in, and all those kind of things, which again will be in the next presentation. And then it really comes back to, believe it or not, the great majority, 90% plus of leaks on pipelines is due to external loading. Engineers typically get the internal loading okay. They design the pipe for the proper inside pressure. But when it comes to the external loading, they don't get the soils right. They use native soil and compact it with PVC pipe, and then the pipe goes beyond that maximum deflection. And on the other hand, engineers also, and I'm an engineer, so I can say these things, they also use a Type 5 trench when speccing ductile iron pipe. Now, if it's under the roadway, it's got to be that way anyway, regardless of the material you use, because you're building a trench for the road. But if it's in an area where that is not a concern, if you put ductile iron pipe in a Type 5 trench, typically you're spending too much money. You don't need to do that. You don't need a Type 5 trench. So.
Great, thanks so much.
Sure.
I think we have time for one more question. Does anyone else from the audience have a question? All right, I'll ask my last question. So does C factor of a pipeline outweigh larger inside diameter with regards to hydraulic efficiency?
Good question. And quite frankly, it's one that is asked quite often when given this type presentation, because even though it clearly shows the inside diameter of ductile iron pipe, it is advantageous hydraulically to that of many other pipeline materials, not just PVC, but other pipeline materials. However, as you saw in this study, and you will see even in the next presentation, the C factor of both pipelines are taken into account. And so effectively, even though the C factor is portrayed to be 140 for ductile iron pipe, 150 for PVC, and quite frankly, they're actually even a lot closer than that together. But we use those factors because that's kind of the industry standard. And so even with a lower C factor, the inside area of the pipeline diameter is much, much more in terms of providing hydraulic efficiency than the C factor.
Right. Thanks so much, Roy. Thanks so much for this wonderful presentation. So now we're going to have a brief 5-minute break while we change to the other speaker. So how about we all come back to the presentation at about 2:10 Eastern time. Make sure you stay within the meeting webinar to earn your full TCH credits. Thanks so much. All right, is just about everybody back, ready for the next presentation?
We're here.
Right, thanks so much. Jeff, are you ready?
I am ready for Roy to present. Absolutely.
All right, go ahead, Roy.
Okay, do you need to do any additional introductions, Sheila?
I don't think so since we did the introductions at the beginning.
Okay.
Perfect, I can see your screen.
Well, I'm trying to share my screen here.
Yep, we can see
Sure.
slide 1.
Yeah, you're shared on our end, Roy.
I'm sorry.
We can see your presentation.
Problem is, I can't see it.
Uh-oh, that's a problem.
Let's see here. Okay, got it. I'm getting a little feedback.
I'm just checking to see if anyone's unmuted to see where the feedback's coming from.
Okay, can you hear me?
No, we still have the feedback.
Let's see. Hello. I'm getting feedback through my. Let me try one thing here.
All right.
Can you hear me? Still
Oh,
getting
we-
feedback.
We can still hear the feedback.
How about now?
It's about the same.
Same. Yep,
Still a little feedback.
yes.
Huh. I'll tell you what, Cielo, I'm gonna leave and come back. Maybe
Okay.
that'll clear that. Okay?
Sure. Thank you. Are you still there, Roy?
Roy, did you make it back in?
I see Roy in the participants list, but I think we lost Roy's mic. All right, I just added Roy back to the chat.
Okay.
We can hear you now, Roy. No feedback.
Good. Okay. Let me share my screen now and see if everything's okay.
All right.
Okay. Can you see that?
Yeah, we can see that, the first slide.
Okay.
Looks good, sounds good.
Everybody, can everybody hear me?
Yep, we can hear you.
Yep, you're good.
Okay. Good. All righty. Well, welcome to the second presentation of our webinar today, which is entitled The Total Cost Equation of Pipeline Material Selection. And once again, I wanted to share our appreciation for allowing the New England AWWA in inviting us to present today. And please don't hesitate to contact us if you have any questions in regard to any issues of pipelines. We really do want to be a resource to you. Approximately 85% of a water utility's capital infrastructure is underground. And I know when I was with American Water, understandably, we would get all excited about building new plants, new boosters, even new office buildings and operation centers. And yet, when it came to pipelines, we knew we had to get from point A to point B. And so we basically went out and even though I think strategically we looked at things a little more so than other utilities in terms of the type of pipe we used, which in fact was ductile iron pipe, and trying to be as environmentally friendly as we could in terms of urban areas and so forth. For the most part, it was a pretty tactical decision getting from point A to point B. However, there really are strategic decisions that should be made when it comes to pipeline material and the selection of that material. And some of those strategic decisions you can see on the screen. Unfortunately, my experience, specifically even after being with McQuane for a little more than a decade now, has been that many utilities basically say, okay, we have to go from point A to point B. We know we need an 8-inch pipeline, so let's go out, see what the cheapest material is we can get. And again, usually it's a comparison of ductile iron and PVC, and whatever comes in cheapest, that's what we're going to put in the ground. And with that type of mindset, quite honestly, many of these components you see on the screen are not taken into account. So therefore, we come back to the issue of life cycle cost analysis, basically trying to address the total cost of ownership, even well beyond the particular cost of the material itself at the outset. About 8 months ago, my daughter called me, and she was in a car dealership here in Lexington. And she said, Dad, I found the new car I want to buy. I think I can afford it. I've talked to the salesperson, and he told me what the payment per month would be, but I want you to come down and look it over and make sure that, it's doesn't have any flaws and so forth. And so, like a good dad, that's what I did. So when I got there, went over the car, and quite frankly, it really did look like it had been well cared for. Looked at the Carfax and all that. I said to my daughter, I said, now you can afford this. That's what you said, right? And she said, yes, I can afford that monthly payment. And I said, well, have you thought about the fact that this particular car you're buying, as opposed to the car you have, will now take premium gas, not regular gas? And, probably 6 years ago, that wasn't quite as big a deal as it has been here lately, but premium gas can easily cost $1 more per gallon than regular gas. Secondly, have you thought about the fact that your insurance is going to go up? Not only because you have a newer car, but you're also going to have the type of car that insurance will go up even more on than the car you had before. Also, this particular car you're getting has a lot of high-end bells and whistles. And I can tell you, when you go repairing or replacing things on this car, then it's going to be more expensive than the other car. And also, again, the type of car that you're getting, this gentleman here in the middle of the screen is going to be looking out for it. And so you're going to have to be careful in terms of how you drive and how fast you drive. Now, even though going through all of that, she basically, we added up the costs, and she ended up buying the car. Her dad actually helped her buy the car, which probably was the reason for the initial phone call anyway. But again, I do what a good dad does. But I shared this story basically to say that the original price of that car went far beyond just the sticker price. And there are other things that should be taken into account, just like when you select pipeline material in terms of your underground infrastructure. So exactly what is this total cost equation? Well, I can tell you that when I first came with McQueen about, again, a little over a decade ago, then I thought this is going to be a dream job. Basically, to go around to talk to people about ductile iron pipe. That's all the pipe I really knew when I was at American Water. It's strong, it's resilient, it's hydraulically efficient. I could go on and on. And so, what's going to be the big deal to that? The reality is, however, many times, even though I'm going to get a lot of positive indication in terms of the quality, resilience, sustainability of ductile iron pipe, before I could leave the room, then there would be a but. But we can't afford ductile iron pipe. Ductile iron pipe is virtually twice as expensive in terms of price per foot than PVC pipe. So my excitement at being here at McQueen, not because I didn't love the company, which I do, but in terms of having basically that easy meeting time after time started to dwindle. And so I thought, just like Paul Harvey says, there's got to be the rest of the story. So effectively, I did sit down with a gentleman. His name is Tom Friley. He was a distribution supervisor that worked with me when I was president of Kentucky American Water. He was a PE, and he understood pipelines. And in fact, his dream was to be a pipeline contractor, which he ended up doing after I took early retirement from American. And so I went and sat with him for an entire day and basically said, Tom, you lay ductile iron pipe, you lay PVC pipe. Is it just all the same after you buy the pipe? And he looked at me and he said, no, I can tell you it's not. And I said, okay, take me through step by step the differences that you have to bid, because that's how you make your living, in terms of when you put in ductile iron pipe and when you put in PVC pipe. So as a result, we created the model mile. Now, I will tell you up front, this model mile is representative of central Kentucky. It will vary, obviously, in certain ways with other parts of the country. It also encapsulates the fact that most of Tom's construction is done in new subdivisions. And so therefore, he lays typically 8-inch pipe. He puts it in subdivisions behind the curb. The lot frontage in those subdivisions for each lot is 65 feet. He also has a tapping crew. They come back and basically after the pipe is put in, and then after the lot is sold and a new house is ready to begin, his tapping crew comes back and taps the pipe and sets the meter. Again, the pipe being behind the curb, so there isn't any paving or anything to deal with. And as I mentioned in our earlier presentation, basically the soil conditions in central Kentucky are very good and are non-corrosive. Basically 80 to 85% of soils in this country are non-corrosive, and that's the way it is here in central Kentucky. Now, another factor we put in our model now, and yes, this is different from other parts of the country, I'm sure, but the fact is Kentucky American Water serves the North American manufacturing plant for Toyota. That's where all the Camrys are made. That's where some of the Corollas are made. They make some Lexus there. And basically, they're the second largest customer for Kentucky American, about 2 million a day, the first largest being, and we love those wasteful students, the University of Kentucky. But anyway, but the bottom line is that the concept of Toyota and their just-in-time delivery concept, there are many, many small manufacturers that have virtually peppered the entire central Kentucky area because they supply parts to Toyota as the car is coming down the assembly line. And many of those facilities require water, and they require water 24 hours a day, 7 days a week. So we incorporated a adjacent facility to this pipeline, which would assume a 695 gallon per minute usage 24/7, because many of these subdivisions are on the outside of the system, and of course that's where these facilities are located as well. So going through the factors that Tom basically indicated beyond the initial bid price of the material itself, you see these particular factors listed on the slide before you in black color. The ones that are in blue color, we're going to discuss. There are issues that Tom obviously understands as an engineer. We incorporated some of them into this model, but at the same time, they're not necessarily representative of anything Tom does, but actually important to the water company itself. So here is the total cost equation. And when you put that equation on the screen, many people initially look and say, boy, that's pretty complex, but it's very, very simple. Probably something many of you are very familiar with when it comes to installing pipelines and the factors included in installing pipelines in a particular area or new subdivision. So we said, okay, we're going to take the approach that a water utility has decided they're going to use this total cost equation in determining what kind of pipe am I going to select for this next 1 mile project in this particular subdivision, and see how it comes out. So let's look at the initial bid price of the pipe itself, and this is material cost only. These are numbers hot off the press, and quite frankly, I appreciate Jeff supplying me with these numbers. Obviously, if you were present for the first presentation, much different than the numbers you saw there. But effectively, the cost of 8-inch ductile iron class 350 pipe is approximately $35 a foot, and the cost of 8-inch PVC pipe DR14 is $25 per foot. And so even though PVC not being quite half the cost of ductile iron pipe, being much more than that, it's still $10 a foot cheaper than ductile iron pipe. And I'm sure most of you all are aware of the fact of the dimension ratio scenario when it comes to how you get a DR18, DR14, DR25 PVC pipe. So looking first at the basics, and we're going to be repeating, and so I'll kind of go through this a little quicker than normal. Some of the issues we talked about that was actually in the University of Michigan study in terms of engineering concept. But basically, when it comes to pipeline designs, underground pipelines that are laid in trenches, you have really two factors. External load, which is the earth backfill, and potentially vehicular loading, which is usually an H20 loading with a loading component of a tractor trailer, if you will, and the internal pressure. What is the maximum working pressure for the pipe? Also coupled with what could be potential surge pressure when it comes to the interior part of the pipe. And the forces that come into play when it comes to attempt to fail the pipe is obviously if you have excessive pressure beyond the pipe capability, the pipe can burst from the inside. And if you have excessive force from the outside, beyond that maximum deflection, you have crushing, whether it be, again, the earth load, traffic load, and so forth. So the flexible conduit theory, actually, which is attached to the names I mentioned earlier, Marston and Spangler, basically indicate that when you have a pipe in a trench and you put a force on top of that pipe, which is, again, the backfill soil load and or even vehicular traffic on top of that, then the pipe, as you see in the upper left-hand corner, is going to want to go oval, is going to want to collapse, if you will, because of that force on the pipe. And so in a very simplistic equation, as you can see on the screen, that pipe deflection, which the pipe deflection, which is a standard acceptable deflection, is 2%. Then anytime you get beyond that acceptable standard, then you are looking at potentially either the pipe starting to leak at the joints because of deflection of the spigot going into the bell, or even failure of the entire pipe itself. So if the load is consistent on a particular pipe, then that pipe deflection is dependent on two things. If you have a stiff pipe, you need less soil loading or less soil stiffness. If the pipe is not that stiff, then ultimately you need more soil stiffness. So as a rule of thumb, when it comes to the soil component of a particular trench, the soil's modulus, which is the E prime you see there, then for ductile iron pipe, even in a type 5 trench, you can get by with 700 psi. On the other hand, when you go to PVC pipe, you've got to have a soil's modulus of a much higher number. Because of that much higher number, you have to construct the trench in a more, shall we say, sophisticated way, which ultimately creates more in terms of cost of the trench. To give you a comparison of the stiffness of ductile iron pipe and the stiffness of PVC pipe, as you can see here, ductile iron pipe, not surprisingly, is geometrically stiffer than that of PVC. So therefore, when in fact you look at these 5 trench types that is defined by AWWA in the M41 manual, then you see as you go to construct each of these trench types, starting with trench type 1 being only digging the trench and putting the pipe in the trench, clear up to type 5, which again is use of select material and so forth. Then as you go from type 1 to type 5, you also go up in money in terms of what it's going to cost to create that particular trench. So when it came to the backfill requirements, and remember the previous presentation that I gave indicated that this particular number was, I think, $3.65 a foot that Tom added to the price of a project when he used PVC pipe just for the bedding costs. You can see that in today's dollars, because these are today's dollars for Tom, that $3 is now $8.60. So he adds $8.60 to every foot of PVC pipe bid in terms of bedding requirements, and nothing for ductile iron pipe because he basically constructs a type 1 trench. We talked in the other presentation as well, and I think I mentioned it in the answer in terms of what really affects pipe once it goes underground, and basically once it goes out of sight, out of mind. Well, these are some common local stress intensifiers, and these are not rocket science. Each of you all are very much aware of these particular components. I will tell you that these components basically have no effect when it comes to the use of ductile iron pipe. Overbelling, basically with ductile iron pipe, if you align the pipe properly, lubricate the pipe properly, and you hear that click when the spigot goes into the bell, that means the joint is tight, it is leak-free. With PVC pipe, however, you can actually push the spigot beyond the bell in terms of where it's supposed to seat in the bell. And then when the pressure is turned on, then that joint starts to maneuver and you can have a leak. When it comes to taps, we're going to be talking about that here in a minute. Effectively, you can tap ductile iron pipe without a saddle. Of course, when it comes to scratches, AWWA says that if there is a scratch on a plastic pipe, whether it be PVC, HDPE, and if that scratch is more than 10% of the thickness of the pipe, then it needs to be discarded. Of course, scratches are irrelevant when it comes to ductile iron pipe. Point source loading. And of course, that's an issue. I was talking about cast iron pipe, that would be an issue because one of the clear advantages of ductile iron pipe, and ductile iron pipe is actually a ductile material classified that way, a flexible pipe, is that cast iron pipe, when put in a point source loading issue, basically it will shear, and you'll see a perfect circle of water coming out when it fails. Because of duct iron pipe having ductility, it will not fail in a point source loading, as you see. And then the last issue, obviously, you're not going to bend duct iron pipe to fit the contour of your project. You are going to have to use fitting. On the other hand, when you install PVC pipe, and there are many contractors who say, hey, I can make that bend using the pipe itself. That means I don't have to put in a fitting. I don't have to put in a thrust block or any kind of restraint. Well, when you put that fitting in the ground in a bent scenario, it creates excessive stress on the external part of the pipe. So anytime that external pipe part of the pipe is disturbed, meaning trying to make a tap on the pipe, for instance, it will virtually just explode, and that stress will create a rectilinear failure along the entire pipe. So, as I mentioned, Tom has tapping crews, and in addition to installing a pipe, he is also contracted to go out and put in new taps with his tapping crew. What you see on the screen is the obvious engineering data when it comes to the particular pull-out forces and moment forces of taps on duct iron pipe versus PVC pipe. And no surprise, because again, of the stiffness and strength of duct iron pipe, much superior to PVC pipe in that particular scenario. However, this is what Tom is more concerned about when it comes to tapping these two pipes. This is language actually out of the JM Eagle PVC brochure and manual. And even though, number one, they contend that, hey, you can tap PVC pipe directly just like you can duct iron pipe, here are the things you do not want to do. You don't want to do that when you're in cold weather. You don't want to do that when you're in hot weather. You definitely don't want to do that if there is a bend in the pipe, as I just mentioned. And the reality is, Tom basically told me, he said, you know, I can't make any money if I've got to go out when it's perfect weather. I can't know if the pipe is bent underground because we may not have installed the pipe or that crew didn't install the pipe. And so the 2x2 or 3x3 hole they do for a tap isn't going to necessarily gauge that bend. And so we might be tapping right into a bend. So effectively, what happens is that Tom will not tap PVC pipe without using a tapping saddle as a factor of safety. And so therefore, when he bids a particular project and that project has a line of taps on it, then he will include $100 for each tap for a tapping saddle, nothing for duct iron pipe. And of course, that does not include the labor to actually put the saddle on the pipe. That's just the tapping saddle cost itself. So we now come into the issue of line locator requirement. Not a big deal, not a big cost. And even though, again, Tom includes it because obviously he wants to include everything he can to make sure he doesn't lose money on a project. The thing that comes to my mind, and we even talked about it, was the fact that when you have a third party digging around a PVC pipe. That pipe has a line locator wire on it. That locator wire is not required for ductile pipe. Ductile pipe can continuously be located without any additional wire or anything. Then the tooth of that backhoe clips that copper wire, pulls it up out of the ground for who knows how many feet on either side. And I can assure you that third party does not put that wire back. They just clip it off on either side and move on. And so you kind of have a hole there in terms of trying to locate PVC pipe. Now, to be fair in this mile of analysis, Tom and I agreed that even though he does not protect ductile iron pipe because he doesn't need to from corrosive environments, we decided that we needed to put into the analysis corrosion protection for ductile iron pipe. And if there's any on the webinar today that has not heard about V-Bio, please get a hold of me or Jeff. We'll be glad to send you information. But effectively, there is a next generation of polyethylene encasement, V-Bio, that is now getting pretty much standard in the industry in protecting ductile iron pipe in corrosive environments. Still extremely economical and extremely easy to use. And so therefore, you can guarantee that corrosion protection is provided for ductile iron pipe. So with that 8 12-inch pipe, V-Bio runs maybe $1 a foot, maybe, it again varies a little bit, very economical. So we put that dollar amount against the ductile iron pipe part of the ledger, so to speak. I'm going to run through the energy component fairly quickly because we've already talked about that in our earlier presentation. Obviously, energy costs are huge line items for almost every water utility, and it's something that most water utilities are very concerned about. As I'd mentioned earlier, actual inside diameters of varying pipe material, as shown here, in almost every case, ductile iron pipe has a more hydraulically efficient inside diameter, inside area as compared to other pipeline material. Obviously, a very dramatic difference is the issue of comparing ductile iron with HDPE, whereby you have a tremendously thick wall. And basically, when you're combining HDPE with ductile iron pipe, you have to go up to the next diameter of HDPE even to equal the hydraulics. So therefore, many times we've been able to downsize the diameter of ductile iron pipe on a project to compete very favorably with HDPE because it has the same hydraulic capability. So I don't mean to insult your intelligence because I know we got some pretty sharp and qualified engineers on the webinar here today, but just to run by a real quick analysis when it comes to an example of ductile iron pipe and its hydraulic comparison to PVC. Basically, you see this schematic. You have a certain gradient with your elevated tank. You can see that you basically have the parameters as you note. And so at the end of the spigot, you're going to have 21 PSI. On the other hand, if you look at PVC pipe, because of the head loss criteria, you're going to have only 8 PSI. That all is due to the fact that you have a lower inside area. What do you have to do to overcome that? If you have PVC, to get to the 21 or 22 PSI, you have to apply energy. Here are some of the actual inside diameters of various pipelines. And of course, we come back to that flow component that I'd mentioned earlier, with the inside area of the pipe being key in terms of velocity and flow. So using, again, the Hayes and Williams formula and going through all of the same thing the University of Michigan went through in determining the present worth of the cost savings to a utility under these particular parameters, which is this amount that Tom and I put forward, and recognizing that 8-inch pipe, duct iron pipe, is 10% approximately larger than PVC, then effectively over the 100-year cycle of the pipe, then a utility would save $80,000 by using duct iron versus PVC. Now, many people may say, well, what's the big deal? $80,000 over 100 years. But remember, you're only putting in an amount of pipe here. So if you continue to increase the amount of pipe in your system, then those dollars could actually get up to the millions as you grow the system, because it does compound. So effectively, here is the results of the total cost equation. And as you see here on the chart, using DR14 versus pressure class 350, then in that mile, even though the initial cost of PVC was $10 per foot less than duct iron pipe, you save for that segment basically $85,000 by using duct iron pipe. Now, if you say, well, I'm not so sure about that energy issue, take energy totally out of it. You're still saving $5,000 using duct iron pipe. Some people say, well, we don't use DR14, we use DR18, which of course is even weaker than DR14. Here is the comparison when it comes to DR18. And effectively, again, if you take the energy out of the equation, then you see that duct iron pipe basically would be about $4 per foot higher than PVC, not $10 per foot. And many utilities would want to go that direction. We did not include mega stops in terms of the total cost equation in terms of overbilling. And we also didn't put support requirements under fittings for PVC pipe that you don't need for duct iron pipe. So effectively, wanted to just indicate that even though we'd like for you to feel free to call me or Jeff on any questions you have about anything, we have a very, very robust website that has well over 100 blogs and videos in terms of how to and answering questions. And I would encourage you to go. And if you have a question about pipe, ductile iron pipe, I would almost bet you're going to get the answer there. So once again, thank you for the opportunity to present today and take any questions that anyone may have.
Thank you so much, Roy, for this presentation. We're a little bit over time, so I think we probably only have time for one question. Did anyone have any? Okay. I had one question for you, real quick before we wrap up. It's what percentage of investments in a water utility comprise its underground infrastructure?
I'm sorry, would you say that one more time?
Sorry, I said what percentage of investments in water utilities comprise its underground infrastructure?
About 85% is underground, and that's kind of startling, quite frankly, to some people. But even though we have big plants and a lot of above ground infrastructure, most of the money goes underground. So.
Right. Well, thanks so much. I'm going to go ahead and wrap up. So I'm going to share our drawing slide for the winner of today's prize. So today's prize was this this journal. And so we're doing the prize based off of who was present the whole time for the questions. And so I have this random prize generator for the two people who asked some questions. So I'm going to go ahead and spin the wheel. All right, congratulations, Jeffrey R. So we'll go ahead and email you this booklet. So thanks so much, everyone, for participating, and we hope to see you at the next webinar.
Thank you.
Very good.
Yeah, of course. Thanks for showing up.
Thank you all. Good to be with you.
Let's see here. All right, can everyone hear me okay?
I can hear you.
All right, great. My name is Ryan Thomas Shea. I'm the Director of Construction for the Boston Water and Sewer Commission. I'm also the Massachusetts delegate for New England AWWA. Very pleased to have you here to discuss sustainable pipeline design. I myself am just going to be not the moderator, excuse me. I'll introduce the moderator, but I'm going to be here for any sort of technical questions and to just make sure that this webinar keeps moving. But without further ado, I would like to introduce the secretary for the New England AWWA section, Ms. Cielo Sharkis. She's going to give a brief intro of both Roy and Jeff, who will proceed forward with our presentation. So, Cielo.
Hi, everybody. Thanks so much, Ryan, for that introduction. I'm going to share my screen now so we can get started. Just 1 minute.
Cielo, I've got on my computer, there are two people in the lobby that need to be admitted.
Okay. Ryan, could you take care of that?
Yeah, you got it. Thank you, Roy.
All right. Can everybody see my screen?